Okay, so we have learned a variety of different integration techniques. We started off with not integration, differentiation. We've learned how to take the derivative. We started off with, how do you take the derivative? Well, it's the limit of the difference quotient. That was like a lot of work. So then we figured out a bunch of rules like the sum rule, the difference rule, the power rule, the product rule, the quotient rule, and then we moved on to the chain rule, which was like um, taking the derivatives of compositions. And I'm going to go to OneNote. We learned a very important thing. Oops. Oh. There we go. We learned a very important thing from the chain rule, especially the Leibnizian way of doing it. We learned that if y, if the variable y is determined by a function f, which has an independent variable u. Okay, right? So what we have here is that y is the dependent variable. And u is the independent variable. And then furthermore, the variable u is from some function g of x. Now notice that u is the dependent variable. And x is the independent variable. That you can now take the derivative of y with respect to x. Now this is a big deal because notice y has u as its independent variable, but you're taking the derivative with respect to x. There's like a mismatch there. So let's just type this down. We need the chain rule to calculate this because there is a quote-unquote mismatch. The independent variable of y is u, not x. Okay, so what the chain rule tells us is that if you want to take the derivative of y with respect to x, you're supposed to be taking it with respect to u. So you have to first take the derivative of y with respect to u. And then what you can multiply it by is the derivative of u with respect to x. And if you think of this as fractions, like basically this du and this du cancels, right, and you're left with dy dx. That's not literally how it works, but you can think of it that way. Okay, so you need to remember this fact. Okay, and it ends up being very useful. So let me give you an example of like where this gets used. So let me show you first of all where it's not used. Let's say that your function f depends on x and you have x squared. You do not need to use the chain rule. If you take the derivative with respect to x. Why? Because the independent variable of f is x, and you're taking the derivative with respect to x. It matches. We are taking the derivative with respect to x, and the independent variable is x. Those match, so you're good. Independent. There we go. So you would just take the derivative and you would get 2x. Here's the problem. Let's say that you have f of u equals u squared. This does need the chain rule. If you want to take the derivative of f with respect to x. Why do you need the chain rule? Because you're taking the derivative with respect to x, but the independent variable is u. They no longer match. So what you have to do is take the derivative of f with respect to u, and then multiply by the derivative of u with respect to x. Now the derivative of f with respect to u is just take the derivative of u squared, that's 2u. when we don't know what du dx is. So you would get 2u times du dx. Notice we took the df du and it became 2u. We don't know what the du dx is. Okay, so this is what we mean by implicit differentiation. This is implicit differentiation. Basically, implicit differentiation is when you are taking the derivative with respect to a variable that is not the independent variable of the function. Yeah, I can't type. In a nutshell, that's implicit differentiation. You have f of u, but you want to take the derivative of f with respect to x. Notice it was f of u, the independent variable is u, but you want to do df dx, that's the derivative with respect to x. The u and the x don't match, you need to use the chain rule.